Hi, this is Kaitlyn Pang, and this is my capstone proposal targeting Trypanosomatid Deoxyhypusine Synthase, a computational approach to drug design. African sleeping sickness, also known as African trypanosomiasis, that I'm going to abbreviate as HAT in this presentation, is a neglected tropical disease caused by a trypanosomatid called Trypanosoma brucei. It is a single-celled extracellular protozoan parasite where they have different subspecies causing different forms of HAT. An example is Gambinese is the most common form, and the best way to explain it is that it creates slow but chronic symptoms, while rhodesine's is the opposite, where it creates fast but acute symptoms. So it's mostly located in sub-Saharan Africa, where the major mode of transmission is the tsetse fly, and symptoms include fever, sleep disturbances, and neurological disorders, where if untreated, progresses into somnolence, severe body wasting, coma, and death. And I would like to mention on the photo below that's really cool, it's bronzescence in a blood smear located from the CDC website. So I wanted to look more into the current treatments in HATs, and I noticed that they have two. NECT, nifurtimox L49 combination therapy, which is DFMO L49, targets the ODC enzyme in the polyamine biosynthesis pathway, where it acts as a suicide inhibitor. And nifurtimox up here, it's not really well studied. It's still currently being studied, but we know that it involves DNA damage and lipid peroxidation. This therapy is considered inadequate because it is difficult to administer, resource and training intensive, high toxicity, and high treatment failures. The latest therapeutic drug, fexindiazole, as you can see similarities with nifurtimox, is an nitroimidazole that is metabolized by NTR or nitroreductase, creating metabolites, and these metabolites show anti-trypanosomal activity. But it's still considered inadequate because it can't treat severe second stages, and it cannot treat children less than 6 years old or less than 20 kilograms. They have to be treated by NECT. So as you can see, there's still room for treatment, improvement of treatment for HAT. And that's why the pharmaceutical industry seek to identify new drug treatments that would produce better efficacy with few side effects exceeding the current treatments. So it led to my question, am I able to find a potential highly selective inhibitor compound that could be a potential drug treatment for HAT? My objectives is that it's easy to administer, low cost of production, decrease in toxicity, and an increase in efficacy. So I began looking for pathways and enzymes that are important in Trypanosoma brucei, and I came across the polyamine biosynthesis pathway. So polyamines are polycationic organic amines that are required for all eukaryotic life. So they're important for cell growth. Spermidine, for example, is a polyamine that is essential in translation, transcription, modulation of chromatin structure, and ion channel function. So it's very essential in the parasitic protozoa. So as I was looking through this pathway, I noticed DHS. DHS interacts with spermidine, NAD+, and E1F5A, also known as the translational elongation factor, to create a deoxyhypusine modification of the elongation factor. And this factor is very important because it's essential protein in yeast, bacteria, and mammalian cells involving mRNA and translation. I would like to also note that the host also has DHS, but you will see later in the slides that they will have structural differences validating DHS as a target enzyme. So I wanted to go more into studying the T. brucei DHS, and it turns out that TBDHS is a tetrameric enzyme where two heterodimers each form a shared active site with a single functional catalytic site and a dead site. But I would like to note that when I mean by dead site, it does not mean that there's no catalytic residues there. There is, because it's able to bind to NAD+. It just means that it's much less compared to the catalytic site of the whole active site. So I'm going to play this video, and it shows the heterodimer where DHSC is the catalytically impaired paralog, and DHSP, the red, is the catalytically dead paralog. where DHSC has most of the key catalytic residues to bind to spermidine, while DHSP has most of the key catalytic residues to bind to NAD+. So when comparing the host from the parasite deoxyhypusine synthase, we can already see a difference. We can see that the human DHS is a homotetramer where the dimer, when together, form two active sites, whereas T. brucei, a heterotetramer, the two dimers form one shared active site where part of it is a catalytic site and part is called a dead site. You can see here in the study that they already compared the active site between the human and T. brucei DHS, and you can see some subtle differences, as well as when you compare, for example, they compared the structure of human DHS with T. brucei DHS, both of the paralogs, and you can see, for example, there's a difference here, which DHSC and human DHS in H7-8, and you can see a difference down here between DHSP and the human DHS. So we're trying to find a difference to help prevent the potential inhibitor compound from binding to human DHS and decrease the toxicity. So it lead me to this statement. Since DHS is an essential in the polyamine biosynthesis pathway and there is a structural difference between human DHS and T. brucei DHS, we would be able to begin predicting a potential drug treatment for HAT using computational molecular dynamic tools. So the next question is, how are we going to apply computational tools? We do it by prepping the system first. And by prepping the system, we create a computational model of the host and the parasite DHS. So we're creating a simulation involving the environment of both the host and parasite DHS. And we're using available crystal structures from past studies using computational molecular dynamic tools. The next step is to identify candidate inhibitor molecules. So by analyzing both the human and the parasite DHS, we can modify these known substrates and drugs to create a better binding with the both parasite DHS and no binding with the human DHS. And then the next step would be to test the binding affinity of these test molecules. So by testing the ligand binding energy and structures, we are able to see whether or not it will strongly bind to, again, the parasite DHS and none or negligible or no binding to the human DHS. And then we would keep repeating until a highly potential candidate is identified. So to summarize, these are my key scientific objectives, is to understand the structural difference between the host and the parasite, a configuration of active site and its binding sites for both host and the parasite, to show the binding affinity between the target enzyme DHS and the potential inhibitory compounds, which we can narrow down choices of potential therapeutic drug compounds for HAT. And lastly, the application of molecular computational tools in the methodology in drug design for vector-borne diseases. There are limitations of molecular mechanics modeling because it is only a classical base time simulation, but these limitations can be seen as the next steps in studying Trypanosoma brucei DHS and the potential inhibitor compounds that are highly selective to T. brucei DHS, but does not bind to the host DHS. So mechanism, we cannot model the breaking of bonds. We can model the conformation and the configuration of the active site, but we can't model the breaking of bonds. We do not know whether it will be metabolized, changing affinity and toxicity. Again, we can model we can simulate the location of where the parasite and the host DHS would be, but we can't model all the enzymes and the proteins located there. So we cannot know if it will be metabolized, changing the binding affinity. And the last thing is we won't be able to see the type inhibitor it is. So we won't be able to see if it's competitive, suicide, non-competitive, etc. These are my references. Thank you for listening.